Good afternoon and welcome to today's video. Today's video is going to be about contour interpolation. Now, the way contour lines are created on a map is simply by mathematical interpolation. Normally the software is doing this all the time in the background when you're creating a digital surface. But the important thing here is that you have to understand what's going on so that if you were ever to have to do it manually, you would be able to do it manually. Furthermore, the greater your working knowledge of how these things are done and how they're created, the better off you're going to be when it comes to working with the computer, giving yourself a feel for how things work and how they should look. Understanding what's going on in the background of any program will help you to be a better user of the program and a much more effective user of the program. So what we're going to talk about today is exactly what happens in the background when a surface model is created. When you go out in the field and survey a piece of property to create a topographic survey, you create a series of shots. It doesn't really matter if you do it the old-fashioned way by hand, if you use Stadia, if you use GPS, if you use a total station. The methodology is irrelevant. The fact of the matter is you create a network of points that exist in 3 dimensions. They have northing, easting, and elevation coordinates, or if you would prefer, X, Y, and Z. In order to create a topographic map, you have to interpolate between those points, because what we use in surveying in the field is generally what's called indirect topographic surveying. For example, say you wanted to draw a contour line at an elevation of 128 feet, for example. Normally, though there are exceptions, normally you wouldn't go out in the field and try to take a point that's at an elevation of 128 feet and then move down several feet or several meters and try to get another point of the same elevation and keep going along. That is what's called direct location of contours. And we do that for special applications, but generally when you're creating a map, you don't do that. What you do in the field is you create points that are not really random. They're at key points or even on a grid, and the point elevations of each point is whatever it happens to be. And then later on in the office, or sometimes even in the software on the data collector you're using, the software will interpolate between those points to determine what the elevation of each contour line should be, or more precisely, more accurately actually, where each contour line will fall between those 2 points. And now I'm going to kind of explain up here on the board a quick and simple explanation before we even get into the math of it. Because remember, when you're trying to think these things out, it's always better to have the concept in your mind before you start crunching numbers. Because if you start crunching numbers without understanding the concept, you're just spinning your wheels. So here we go. We're going to give you an example. Now, you're looking at this. Imagine looking at this from a side view, the side of a hill. That's one way to put it. You're looking at the side of the hill. And up here, you have the top of the hill. And then the hill kind of comes down to a slope. And then there's the bottom of the hill, just like that. Very, very simple. Very simple concept. Just for the sake of this example, let's just say you know the elevation at the top of the hill. Know the elevation at the bottom of the hill. And then it's up to the software or you mathematically to figure out what the points should be that have a given elevation. Because remember, the definition of a contour line is a line which connects points of equal elevation. Well, looking at our example here, let's say the top of the hill has an elevation of 128 feet. How's that? And the bottom of the hill has an elevation of 124 feet. Well, between 128 and 124, assuming we want whole numbers, which is very common, 1 foot elevations are common, we don't even have to do the math on this one. It's obvious that if that's 124 and that's 128, and that line is basically straight between the 2 points, that 126 will be right in the middle. And then 125 will be halfway between 126 and 124. And 127 will be here. And that's basically what is happening when a contour map is created. The question is, how does the math work? This was really, really easy. And I did it that way on purpose because I didn't want to get bogged down in the math. You have even numbers and even whole numbers and an even division of the line. So what we're going to do now is go into a little bit more complicated a situation, and we're going to look at it a little bit differently. Excuse me while I erase and see if I can. Okay, here we go. We are going to take a much more detailed example of interpolation here. Here we've got a hill. Again, you're looking at the side view of a hill. The top elevation, 426.5. The bottom elevation, 417.2. And right here, we've got the formula that we are going to use to interpolate where along this line the contour points will fall. And that formula is very simple. X equals D times Ex minus E min over E max minus E min. In this formula right here, D is the horizontal distance between these points. In the case of our example here, it's 38 feet. Ex is the elevation you're solving for. We're going to start at the bottom of the hill, work our way up, and the next elevation we'll be solving for, in this case, will be 418. E min is the elevation at the bottom of the hill, E max is the elevation at the top. Very simple interpolation, and we're going to give it a run right now. To solve for the first whole number, which in this case will be 418, we're going to simply do this. X is going to equal 38 times 418 over 4 minus 417.2 divided by 426.5 minus 417.2 very straightforward. We can do the math and we're going to reduce it and write it down below. We don't have that much real estate to work with here. So we're going to write it down below. X is going to equal 38 times 0.8 divided by, what would that be, 9.3? 9.3. And that is going to give you, let's do some quick math here. Quick math gives you 3.27. We're just going to round that to 3.3 feet. We're not going to get that precise. 3.3 feet is good enough. So what that tells us is that the 418 contour is going to fall 3.3 feet horizontally below the, above the toe of the slope, or the bottom of the hill if you prefer. 3.3 feet. Now, normally be on paper, you'd be scaling this very precisely. Here I'm kind of eyeballing the distance, and it's probably going to be a little bit off, but we're going to do the best we can. 3.3 feet is going to be a little less than 1/10 of that distance. So I'm going to say that it's right here, and that'll be 418. Now, what you can do, if you would prefer, is repeat this process over and over again all the way to the top. And that's a very effective way of doing it. But we're going to do a bit of a shortcut method. And that shortcut method is based on the concept that if this is a straight slope, and we always assume that it is when you're interpolating between these points, because you have to. If it were not a straight slope, you'd have more points in there. Assuming it's a straight slope, the horizontal distance between every 1 foot vertical interval will always be the same. If you go over a certain distance and go up 1 foot, you can keep going over that same distance to go up 1 foot. So that means we got another calculation to do, and that is to find out how far we go horizontally to go up 1 foot. And we're just going to adapt the formula we've got right here. So x, in this case, for 1 foot, is going to equal 38 times 1 over 9.3. Do the math. That gives you a horizontal distance. That gives you a horizontal distance between 1 foot contours of 4.08 feet. And we're just going to say 4.1. And that looks like kind of the right kind of number, because here we went 8/10 of a foot vertically. We went over 3.3. Here we're going 20% further. We should be going, or 20% higher. We should be going 20% further. And that works out just about right in round numbers. Now that you know that number, that 4.1, well, you can just duplicate that over and over all up the line. Excuse my measuring dividers here. I'm just going to use my fingers. If that's 3.3, 20% more, that'll give you 1, 2, 3, 4. No, that's going to be less. I'm just going to estimate my distance between these points because, like I said, I don't have a scale. So 4 feet, if that's 3 feet, 4 feet is going to be basically the same distance. We're going to do, that'll be 419, 420. Yeah, that'll work out. Just going to do it this way. We're going to say that's 419, 420, 419, 420, 421, 422, and so on. We didn't quite scale it right here. $424. We didn't quite scale it right because, like I said, I'm not working with a scale. But the concept is the same. You basically do the math to get yourself on an even foot. Do the math to figure out what the interval between the even foot contours is. And then you just basically duplicate that all the way up the hill. Now here I didn't quite draw it in here correctly, so I'm going to cheat a little bit, which I don't feel bad about given the limitations of what we're doing here. We're going to erase this, and we're going to raise it up a little bit more. Once again, normally you would not do this. The points are what they are. Make 426.5 back up here. 426.5 right there. And that'll be 425 will be here, and 426 will be here. And that is how the concept of interpolation works. Now, when you get up here to the top of the slope, you have to check in and make sure you got the right distance. If, to use our example, if you know these are roughly 4 feet apart and you get up here at the top of the hill and you still have a gap that would qualify as 6 feet, you know you did something wrong and you have to go back and check yourself. It's one of the things that we try to do as part of any process. As you work your way through, you're constantly checking to see if what you've done looks right. Sometimes you've got to mathematically check it. In this case, occasionally you will. But more often than not, for something like this, once you've done it a few times, you get a feel for it, you develop a skill for it, and you won't have to do the math. You'll be able to look at it and say, that looks right, or that doesn't look right. That applies both to this and pretty much everything else you do in this business. It doesn't matter if it's surveying, civil engineering. The numbers say something, and the numbers don't lie, they say. But occasionally, you'll come up with a number, and you'll look at that number, and you'll say, there is no way that's right. I did something wrong. And there's nothing wrong with that. That's just part of the process. You just have to go back, look at it, and see if it is. It may be that your instinct, what your instinct or your professional judgment tells you looks right, doesn't match with the actual numbers when you've done it properly. But if you ever go through this process or any other process in this business, and you get to the end and the answer just doesn't seem right to you, that is your instinct, your professional knowledge, telling you to go back and check to make sure that you didn't miss something, you didn't overlook something, or you didn't just make an error. It's a natural part of the process, and it's one that you need to be comfortable with and used to. The worst thing you can do in this business, whether it's surveying, civil engineering, or pretty much any other technical field, is coming up with a number and assuming that that number is gospel without checking it. And we have ways of checking and checking back in. And that's an important part of what we're doing here. Now, in a minute, I'm going to show you a slightly different way of approaching this same problem. This was pretty cool because I was teaching a class the other night and a student had a question, and he wanted to understand how this process was going. And I used a slightly different method to illustrate this same thing that we're doing here. And in the process of using that different method, I came up with a slightly different way of interpolating the contours. I mean, the math is basically the same, but it's a different approach, and it may be one that helps you in your quest to understand what's going on. Give me just a minute. We'll start another video. Alternate way of computing contours, and maybe that'll help. Just keep working at it until you get it right. You know you can do this. I believe in you. you need to believe in you too. Okay, here we go. We are going to look at a way of interpolating contour lines along a slope. Now, you may have watched my other video where I interpolate contour lines. What I'm going to show you now is a slightly different way of doing the same thing. Now, the way I taught in my other video is the way I was taught when I took this stuff in school back in the dark ages, when I first started getting into the profession. But I had a student who was trying to understand the concept of what was going on just the other day. And in the process of trying to illustrate to him what was going on, in the process of doing that, I came at a completely different approach to interpolating contours. And just for the heck of it, we're going to go over that right now. I'm going to use it, I'm going to demonstrate it, and it may be going forward you use it too. It's a perfectly legitimate way of doing it. It's just different. And you know what? If it helps some people understand what's going on that otherwise wouldn't be able to understand what's going on, then that's a victory. So here we go, an alternate method of interpolating contours. Now, here we have basically the same problem we had before. We have a point at the toe of the slope, or the bottom of the slope if you would prefer, and a point at the top of the slope. These points have an elevation of 426.5 and 417.2. And the horizontal distance between them is 38 feet. Now I'm using feet because that's what I'm accustomed to. And that's what we use here in the United States of America. If you're somewhere else in the world and you're doing this in meters or any other unit of measure, basically the math is going to be the same. So don't let the feet put you off. So here we go. The first thing we need to do is look at this line and think of it in terms of the rate of change. So I'm going to wing this as I put it up here. I mean, I know how I'm going to do this, but I've never stood in front of a camera and done it before. So this problem, like all of my other problems, is shot from it's shot from the hip. I don't make these things up in advance. I don't rehearse. I don't script them. Even in my classroom when I'm standing in front of my students, every problem I do, I make up on the fly on the board. That way nobody knows the answer going in, and it makes it a lot more fun. It'd be insanely boring to stand up there and write down a question to which you already knew the answer. So here we are. The first thing we need to do is figure out the rate of change. So the rate of change in this case, the rate of change of elevation is simple. It's the change in elevation over the horizontal distance. Horizontal distance. The change in elevation over the horizontal distance. So in this case, our change of elevation was 9.3 feet. I'm going to abbreviate the rate of change as the ROC. O with the little apostrophe on it there, just for fun. Our delta elevation between 426.5 417.2 is 9.3 feet. And our horizontal distance between the 2 points is 38 feet. And we're going to do the math here. Plus 0.24. And because this is feet divided by feet, that is in feet per foot. So our rate of change in this particular situation is 0.24 feet per foot. Very interesting information, important conceptually, But how the heck does that help us get to our contours? Well, that's where you just take this same formula and you just flip it around a little bit. If our rate of change is the delta elevation over the horizontal distance, well, that's going to apply for any segment of this whole slope here, because the rate of change is going to be the same. So if ROC is going to equal delta elevation over HD, I'll just put HD for horizontal distance, save some space. Well, our goal here in interpolation is to determine where the 418 point is going to be along this line. So that's an HD. We're trying to solve for a horizontal distance. Well, we already got a formula. If ROC is delta elevation over HD, then HD has got to equal delta elevation over ROC. Rate of change. Well, how does that work out mathematically? Well, our delta elevation, the first contour line, or the first even contour line we want to solve for, along this line is the first whole number, which will be 418. So, we're going to try to solve for horizontal distance. First, we got to solve for delta elevation. So delta elevation is going to equal 418 minus 417.2, which is 0.8. Take that number and plug and chug in here. HD is going to equal 0.8 divided by our rate of change, 0.24. 0.8 divided by 0.24 is 4.16. 4.17. We're just going to let that be 4.2. All right, that's certainly good enough. We're not getting into the hundredths or the thousandths of a foot here. It's a contour map. You know, don't fool yourself by being too precise. If you get too precise with numbers, I mean, this is fundamental surveying. If you get too precise with your numbers, you're kind of lying. You're implying a level of precision that simply is not there. And we're not going to do that here. 4.2 is good enough. So here we go. The delta elevation, or excuse me, the horizontal distance for a delta elevation of 1 foot is 4.2 feet. So we could take that 4.2 feet and just replicate it all the way up the line here. Now, I don't have, once again, I don't have a scale or anything like that, so I'm kind of eyeballing the distances. But we can come up here. I'm going to do my best to eyeball it and keep it even. We can do up here, we'll put 419, 420, 421, 422, 423, 424, and 425. And that gives us a little bit of a gap to 426.5. Now, like I said, this is not to scale, but even at this point, just looking at it, I can see that my distance here between these 2 points is, well, it's a little bit better than half of the distance between the even contours. I'm going up a foot here. Here I'm only going up half a foot. So theoretically, this distance should be, the distance from here to here should be half of that distance. I can look at it and tell it's not exactly half. It's a little bit more than half. But it's certainly close enough in this particular case. Close enough for our example. Once again, if I had a piece of paper, a drafting table, and a scale, I'd be doing this a whole lot more precisely. But that's irrelevant. That doesn't teach you how to do it any better. It just draws a better map. And the point of this video is to show you how to do it. So that is the alternative method for determining contours. In a way, it is simpler if it helps you understand it better. By all means, go for it. The important thing is that it works. In this case, it kind of works. In a strange way, it's simpler than the other way. I'm used to doing it the other way. But this is a whole heck of a lot simpler. And if it gets you the right result, and it works, have at it. So there you have the alternative method for finding contours. I hope you found this video informative. I appreciate your time, and I look forward to doing some more videos for you to help you learn all this kind of stuff. Thank you for your time, and have a good day.